Look, the Artemis crew just flew around the moon and something genuinely unexpected happened. They watched bright flashes light up the lunar surface while they were passing through a solar eclipse. Now, the moment I say that, your mind probably goes to UFOs or hidden bases or something strange. Wrong. And that's the interesting part. It's not wrong because it's less exciting than aliens. It's wrong because we actually understand what's happening, and that understanding is far more revealing about how we fool ourselves. Here's what they saw. Flashes of light on the moon's far side visible during the eclipse on April 6th. Reed Wiseman and the crew reported seeing these luminous events happening in real time. The first humans to witness this in more than 50 years. And immediately people started searching for extraordinary explanations. But here's the trap we fall into. We start with observation and work backward to find something mysterious. We should do the opposite. What does mystery actually mean in physics? It doesn't mean unexplained. It means explained by false ideas. Most of what we call mysteries are just observations we're looking at the wrong way. We rename the problem and call it a solution. But understanding means something specific. Being able to predict what will happen next. Being able to measure things. Being able to say, if this is true, then that will follow. And then watching it happen exactly. Meteoroids hit the moon constantly. I mean constantly. A speck of rock traveling at 40 to 70 kilometers per second, faster than a rifle bullet by many times, crashes into the surface. What happens? It doesn't bounce. The kinetic energy releases as heat and light in microseconds. You get a flash. That's it. The surface of the moon is continuously bombarded by this, billions of impacts every single day. We see evidence everywhere. Craters, dust, pitted surface. Every impact feature is kinetic energy converting to light and heat. Why don't we see these flashes from Earth? Several reasons. First, the moon's horizon blocks most impacts from view. You're looking at a curved surface from 384,000 kilometers away. Second, the moon has an exosphere, extremely thin, mostly sodium vapor, no air to glow. On Earth, a meteor glows because our thick atmosphere heats up and emits light. On the moon, there's no atmosphere. The impact itself produces the light, direct energy conversion. And third, the ground is dark. The lunar surface is covered in regolith, fine dust created by billions of years of impacts grinding rock to powder. This dust absorbs light. A flash lasts microseconds. In those microseconds, temperature spikes to thousands of Kelvin. Plasma forms, light bursts out. But from Earth, looking through vacuum to detect a microsecond flash on a dark, distant surface, technically possible, practically impossible. The signal disappears in the noise. But here's the revelation. The Artemis crew was positioned completely differently. They weren't looking up from beneath. They were flying past the moon, 432 kilometers from the surface. Close enough that the moon filled their vision, and they were positioned during a solar eclipse. The sun was blocked. The surface was dark. Perfect observing conditions. The flash, bright and sudden, stands out against a completely black background. From Earth, the sky around the moon is bright, solar glare, atmospheric scattering. But from Orion, in eclipse, you get a black background and a clear view of impacts happening in real time. Now here's what's actually interesting. We predicted this should happen. Physics predicted it. We calculated that these flashes occur maybe 3 to 4 times per day somewhere on the moon. The crew saw several in a few hours because they had a direct, unobstructed view during perfect conditions. This isn't a surprise. It's confirmation of prediction. We've detected similar flashes, other ways. Photomultiplier tubes, some telescopes. But this was the first time humans directly observed them with human eyes. That's different from discovery. Discovery is when reality surprises your prediction. Observation is when you see what you expected to see, but more clearly than before. Why should you care about that distinction? Because it changes what the observation means. If these flashes were unexpected, if the moon was suddenly producing light in ways we didn't predict, that would be genuinely strange. But they're not. They're the same process we already understand, now made visible in the right way at the right place. The phenomenon didn't change. Our ability to observe it changed. But the Artemis crew reported other things too. Unusual colors on the lunar surface, green patches, brown regions, gray areas where we expected monotonous gray regolith. They described craters that looked dusted with snow. They saw patterns they called squiggles. And immediately, people start hunting for explanations. Is it water ice we missed? Geological process we don't understand? Chemical changes on the surface? Let me be direct. I don't know what those colors represent, But I noticed something important. The astronauts are seeing things from a vantage point no human has occupied in over 50 years. The lighting is different from space than from the ground. The angular resolution is better. The human eye perceives color differently than our satellites measure wavelengths. We have gaps in our satellite coverage, especially near the poles. Our instruments have limitations. The human eye sees in real time what photons are actually bouncing off the surface. Could those colors represent something genuinely new? Yes. Could they represent geological features we've never examined carefully from this angle? Also yes. Could they be optical artifacts or processing effects? Possible. The point is, we should be excited about new observations because they're detailed and give us information we didn't have. But we shouldn't confuse novelty with strangeness. Humans seeing something for the first time doesn't mean that something just started existing. It means humans are seeing something. The real physics underneath impact flashes is straightforward. A meteoroid weighing 100 grams hits at 40 kilometers per second. That's 10 times a rifle bullet's speed. The kinetic energy is 1/2 times mass times velocity squared. 1/2 times 0.1 kilograms times 40,000 meters per second squared. That's 80 megajoules. That's 20 tons of TNT released in microseconds in a volume the size of a marble. The temperature reaches tens of thousands of Kelvin. Everything becomes plasma, ionized gas. Plasma emits light, the energy drops. The plasma cools, the light fades. Microseconds, over. That's not mysterious. It's familiar physics. Collision, energy transfer, heat, light. The same process that makes a light bulb filament glow, just scaled up on a lifeless world without air to scatter the photons. We understand this process completely. We can predict it. We can measure it. We can recognize it for what it is. But here's what transforms understanding. The moon is not quiet. The moon is not dead. It's continuously pummeled by the solar system. Every second, dust hits it. Every minute, larger pieces impact it. Every day, bright flashes light up the surface. Every year, new craters form. The moon that Apollo saw isn't the same anymore, not visibly to us, but in ways that over billions of years completely rework the surface. When we think about the moon, we think ancient history, frozen landscape, rock sitting in space doing nothing. But that's because change on the moon is slow by our standards. We live 80 years. The moon is 4.5 billion years old. The time scale is incomprehensible, but the processes are identical to Earth. Both are continuously transformed. The only difference is pace. Earth's atmosphere and water create rapid visible change. The moon's lack of atmosphere means change is imperceptible on human timescales, but it's happening constantly. This is the first transformation in understanding. Unexplained doesn't mean magical. It means not yet integrated into our framework. When we gather more information, when we look from different angles, when we position ourselves better, the unexplained becomes ordinary. The strange becomes familiar. The moon doesn't change. Our knowledge changes. Now here's something that deserves more attention. The astronauts' descriptions didn't initially match what ground instruments showed, and people had to figure out why. This is crucial to understanding how science actually works. Instruments are limited. A spectrometer measures light in particular wavelengths. A thermal camera measures heat. A radar measures reflectivity. But they don't measure everything. The human eye sees color differently than spectrometers interpret wavelength. We see contrast. We see patterns instruments might miss. We see holistically. So when observations didn't match, it wasn't that either the instruments or humans were wrong. They were measuring different things, capturing different aspects of reality. This tells us something important. Our understanding of the moon is incomplete. Not wrong. Incomplete. We have gaps. We have blind spots. Things we haven't examined carefully. The lunar surface has features we thought we understood. Regolith, craters, highland regions, Maria. We thought we'd mapped everything. We thought we knew the composition. But satellites look in specific ways. They orbit at specific altitudes. They take pictures at specific times. They have specific sensitivities. They miss things. A human observer flying past at different speed, different angle, different lighting, with different sensitivities, will see things satellites miss. This is true for all of science. We never see the complete picture. We see what our instruments show us. We build models from that data. Reality always has more to teach us. There's always another layer, always a detail we missed, always a pattern visible only from a different angle. The snowy craters that astronauts described. This matters specifically. Water ice exists on the moon. We know this now, we've detected it. It persists in permanently shadowed craters near the poles where temperatures drop below -170 Celsius, but astronauts saw bright features in places where we didn't expect ice. If they genuinely observed material looking like frost, we have possibilities. Either we missed ice in those regions, or conditions are different than we thought, or we need to reconsider what creates bright regolith features, or it's something else entirely that looks like snow but isn't. That's not a mystery, that's an observational gap. We need to investigate, we need to look more carefully, we need to take spectrographic data, we need to understand what they observed, and in doing so, we'll improve our understanding of the moon. But here's what shouldn't transform your understanding: the idea that the moon is suddenly becoming active or strange. It isn't. It's always been continuously bombarded. It's always been transforming. We're just seeing it more clearly now. The change isn't in the moon. The change is in us, in our vantage point, in our ability to observe. And that recognition is important because it reveals how we think about the universe. We're drawn to permanent features. Craters endure. Mountains are stable. Landscapes persist. The regolith seems undisturbed. But actually, the moon is being continuously reworked. Micrometeorites hit the surface constantly, billions per day. They pulverize rock. They create new craters. They shift dust. They create new exposure of subsurface material. Over billions of years, this completely transforms the surface. We understand this intellectually, but there's a difference between intellectual understanding and witnessing it. When the Artemis astronauts saw those flashes, they witnessed the process in real time. They saw the moon not as a fossil of its past, but as an object undergoing continuous transformation. They saw light released from impacts. They saw the surface being shaped by forces actively working. Right now, at this moment, while we're watching, this changes how you think about celestial bodies. Earth seems alive because change is visible and fast. Water flows. Weather happens. Organisms move. Earthquakes shake the ground. The moon seems dead because change is imperceptible on human timescales. But both are continuously transformed by the same forces. Both are being bombarded by meteorites. Both have material ejected from impacts. Both have chemistry altered by radiation. Both have geology rearranged by impacts. The difference is entirely in the speed of processes relative to our lifespan. On Earth, erosion is visible. Wind shapes rocks over decades. Water carves canyons over millions of years. On the moon, the same processes operate. No weathering, no running water, but continuous bombardment. The bright craters are young. The dark craters are old. Their bright ejecta darkened by radiation over time. The surface is a geological timeline written in impacts. When you understand this, the Artemis observations take on weight. They're not just seeing flashes, they're seeing the writing of the timeline. They're seeing the moon in the present tense. Not as history, not as ancient landscape, but as a world undergoing change. Why did NASA scientists find astronauts' descriptions difficult to match with ground observations? Fundamental measurement problem. Ground-based telescopes and orbital instruments have specific capabilities. They sample the lunar surface continuously, but with particular sensitivities and blind spots. A telescope looking from Earth sees what its optics allow, the wavelengths it can detect, the resolution it can achieve. The Artemis crew has human eyes, different sensitivity curves, different color perception. They're positioned differently. They move at different speed relative to the moon. They're close enough to see details distant satellites can't resolve. When observations don't match, it's not because reality is inconsistent. It's because our instruments reveal different aspects of reality depending on where they're positioned and what they're designed to detect. This teaches something important. The moon isn't weird if we see something unexpected. It's poorly understood by our particular observational method. We have gaps. Our instruments have limitations. Our satellites orbit at certain altitudes and take pictures at certain times. They don't see everything. No single observational method captures the complete picture. The green, brown, and gray colors the astronauts reported, Joel Kearns from NASA said they could indicate mineral variations or surface composition changes. But honest answer, we don't know yet. We have spectrographic data from orbiters, but human eye perceives color differently than spectrometers interpret wavelength. What humans describe as green might be iron oxide and olivine minerals reflecting certain wavelength, or optical illusion from contrast, or something else entirely. We need to examine observations carefully, compare with instrument data, and see where they overlap and where they contradict. That process, that's where new understanding comes from. Gather observation from new angle. Compare with existing data. Identify mismatches. Ask why the mismatch exists. Design new observations to resolve it. Build new model incorporating everything. Test that model. Look for the next layer of complexity. That's the actual work of science. It's patient and methodical and unglamorous, but it's how we learn. The broader lesson here is how we interact with the unknown. When something is unexplained, temptation is to invoke something extraordinary. Unknown equals mysterious equals possibly exotic equals interesting. But usually, unknown just means we haven't looked carefully enough, or we've looked from the wrong angle, or our instruments miss something that direct observation captures, or we don't have enough data to integrate the observation into our existing framework. The universe isn't weirder than expected. We're usually just seeing familiar physics operating in environments we haven't examined closely. The environments change what we can observe. The vantage point changes what we can see. The instruments we use determine what we measure. These limitations combine to create gaps in knowledge. Those gaps feel like mysteries until we fill them in. But here's what does transform understanding. The realization that the moon, which seemed unchanging and dead, is actually a continuously evolving surface shaped by constant bombardment. The flashes the Artemis crew saw aren't evidence of something new. They're evidence of something continuous, now made visible. Making visible a process that's been happening for 4.5 billion years, every second of every day, for as long as the moon has existed. Think about that for a moment. The moon has been forming impact craters and being bombarded by meteorites for 4.5 billion years. That's a number so large it's difficult to grasp. 4,500,000,000 years. In that time, the number of impacts is incalculable. The total energy released is incomprehensible. The amount of dust created is beyond measurement. The surface has been completely reworked multiple times. The craters have been filled in by later impacts. The dust has been blown around by more impacts. The composition has been altered by radiation. The landscape has changed completely. And we're just now, for the first time in more than 50 years, looking at it with human eyes positioned to actually see what's happening. The observations from Artemis 2 give us something precious, a moment captured. A snapshot of real time on another world. We've sent thousands of spacecraft to the moon. We've taken millions of pictures, but mostly from orbit or from robotic rovers. Rarely from humans positioned between the moon and Earth, flying around the lunar surface, watching it directly. The last time was Apollo 17 in 1972, more than 50 years ago. 50 years of new craters, 50 years of surface change, 50 years of the moon continuing to be bombarded while we weren't watching closely, and now we are watching. And what we're seeing is that the moon is not quiet, the moon is not static, it's a world undergoing continuous transformation. But there's another layer here that matters even more. We assumed the observations we were getting from satellites and ground instruments were complete. We thought we knew the moon, we had maps, we had compositional data, we had crater ages, we had theories about formation and evolution. We thought the problem was solved. We thought the moon was understood. And then humans go back, and they see things we missed. Colors we didn't expect. Features we didn't catalog properly. Flashes we never observed directly before. This reveals something uncomfortable. We don't know what we don't know. We have blind spots. Our satellites have limitations. Our instruments have wavelengths they can and cannot measure. Our theories are built on incomplete data. We filled gaps with assumptions. We drew lines on maps where we didn't have complete information. We marked regions as understood when really we just had a satellite image. We thought we were done. This pattern repeats throughout science. We gather data. We build models. We test predictions. The models work. We think we understand. Then we get new data from a different vantage point, and the models need revision. Not complete replacement usually, but adjustment, refinement, expansion. The models were mostly right, but not completely right. Incomplete. Missing something. History of science is full of these moments. We thought atoms were indivisible. Then we found electrons. We thought electrons orbited nuclei, like planets around the sun. Then we found they behave like probability clouds. We thought the solar system was the entire universe. Then we found galaxies. We thought the universe was static. Then we found it was expanding. We thought the moon was dead. Now we're watching it be bombarded in real time. Each time we thought we understood. Each time we were incomplete. Each time new observations from a new angle revealed complexity we'd missed. This pattern is so consistent, it suggests something important. Our understanding is always incomplete. There's always another layer. There's always something we haven't seen. The question isn't whether we're missing something. The question is what. For the moon, that something is now coming into focus. The Artemis observations are the beginning. We're going back. We're planning new missions. We're going to land on the far side. We're going to explore the poles. We're going to look for water. We're going to study the impacts and the geology and the composition. We're going to ask new questions, and those new questions will reveal new gaps in our understanding, and we'll build new models, and we'll refine our knowledge. This is the actual process of science, not revelation, not sudden insight, not one brilliant experiment answering everything. Steady, methodical, relentless refinement, one observation at a time, one question at a time, one layer of complexity at a time. The Artemis crew brought back something else. They brought back the perspective of human eyes and human minds, positioned to observe and interpret. That's not something you can fully automate. A robot follows a program. It collects data according to its programming. But a human looks around and thinks, that's odd, I wonder what that is. A human asks questions. A program wouldn't ask. A human makes connections. A robot wouldn't make. A human remembers what they saw in one place and compares it with what they see in another place and asks why they're different. That's the power of having humans return to space exploration. It's not just romance or adventure. It's the cognitive capability to observe and interpret in ways that machines can't replicate. It's asking the questions that programs weren't written to ask. It's seeing patterns that statistical analysis misses. It's the human brain encountering the universe and being surprised by it. And that's why these observations matter, not just as data points, but as observations from human cognition positioned to witness the moon, questions asked by people who were there, comparisons made by brains that could see the whole landscape and understand it as a place. The Artemis observations demonstrate that there's still much to learn about the moon. They show that human cognition adds value to space exploration. They show that having people in space, paying attention, asking questions, making observations is worthwhile. And they show that the universe is still surprising us. We thought we understood the moon, we had it catalogued, and then we sent humans back, and they saw things we'd missed. The moon sits above us in the sky. We've been there. We've brought back rocks. We've studied it from satellites. We have maps and compositions and ages. We thought we were done, and then humans returned, and they saw things we'd missed, and we realized that the moon, which seemed to be solved, is actually still full of questions. And that's the real significance